Hi everyone, thanks for joining in for this presentation. The title of this presentation is a strategy for fine mesh resolution in contact mechanics. My name is Gaurav Chauda. I am a senior PhD student at at Michigan State University. I have done this research with my professor Daniel Segalman. So motivation for this research comes out to be from the computational cost for the contact analysis, because the computation cost for each contact iteration goes as n to the power alpha, where alpha varies from 2.4 to 3. And as n is the number of degrees of freedom of the system, as n increases, your computational cost increases. The other thing is an extremely fine mesh is required to conduct a contact analysis between two surfaces. And the finite element method is the most common approach, but it requires many degrees of freedom inside the body. So for example, we have two cylinders pushed against each other, and the contact surface is discretized with 40 nodes in 4 degree of contact surface. Then it can lead to 4,404 nodes over the cylinders for a fairly coarse mesh. So if one want to put 100 nodes over a 1 degree of contact patch, then it can lead to tens of thousands nodes. Boundary integral element method is another method, but it also have the more nodes than the far more nodes than the contact nodes. So here is the big idea to create a compliance matrix that permits us to drop all the equations associated with nodes that are not in contact or otherwise not subject to load. So for example, if we have a compliance matrix, we multiply it with the pressure field or traction field that will result in the displacement field. So if we have a two set where set A refers to the nodes which are in contact or in the contact region, which we are going to expect, and no B refers to the set of nodes which are never going to come into contact. So if these traction will always be zero, then we can drop out these column of contact column of compliance metrics and also this row of compliance metrics. That reduces our compliance metrics to a small compliance metrics and result in a small set of uh, equations. So now the question comes up, for which geometries can we calculate the compliance metrics easily? So there are very few geometry. One is elastic half plane, and the another one is two-dimensional disks and holes, and which is and this study is presented here. So the basic strategy is first to choose a basis function for the traction on the surface of disk or the hole, and then expand this basis function as a Fourier series. Also, on the other hand, identify the Michel's Airy stress function coefficient and corresponding to that Fourier series, and sum the Michel solution to obtain Fourier series for the traction and displacement. Compare the Fourier series of traction with Michel Fourier series, and deduce the Michel coefficient. And after deducing the Michel coefficient, calculate the displacement at all the nodes, and this displacement will be the one of the column of compliance metrics. So for an example, if we have elastic disk and we discretize it in very small interval, and let's say we identify our contact region from minus theta to theta, then we can implement a unit traction on one of that interval, which can be shown here. So if we implement a unit box function on that interval, that can result in a corresponding displacement, which is shown in the dashed line. Due to symmetry of the elastic disk, shifting a radial traction result in a shifting of displacement field too. So by that way, we can calculate displacement field for each node. And by assembling these displacement field together, we can create a compliance matrix. So here is the compliance matrix that we use for our problem. Here we added 3 more rows and 3 columns. They are added to equilibrate the forces and the movement with uh, radial and tangential traction. And also we added 3 rigid body constant. The important things to note here that only nodes in contacts are used to formulate the equation of motions and needed to be solved for the contact analysis. Therefore, the columns with nodes not in contact can be discarded for the analysis, and that can reduce the size of compliance metrics and the complexity, reduce the complexity of the problem. Other benefit is like decoupling approximation can be easily implemented using the compliance metrics. Uh, by making CR theta equal to 0, we can apply the Goodman decoupling approximation, which is that your tangential displacement is not going to affect your radial traction. We can set full decoupling by setting CR theta equal to 0 and C theta r equal to 0. So for comparison, we choose two identical cylinders which are pushed against each other. So in first case, the identical cylinders are pushed with a normal force. In the second case, first they are pushed against each other and then sheared, while we are employing the one parameter Coulomb friction with static coefficient of friction to be 0.7. In the third case, the same problem, but we employ the two parameter Coulomb friction where static coefficient of friction is 0.7 and kinematic coefficient of friction is 0.5. For first two cases, we have analytic solutions, but for the third case, we do not have analytic solution. But first two cases, the analytical solution is only possible with the Goodman decoupling approximation. So for the comparison, for all three, we implemented Goodman decoupling approximation with all three cases. So after applying, after solving for the contact analysis, that result in traction and displacement. So for the first case, when there is a normal contact only, the normal pressure distribution numerically comes out to be exact in line with the analytical normal distribution. Also, in that case, there is no slip between the two contacting surface, so the resulting lateral traction comes out to be 0.2. Also, when we apply the lateral traction, that generate when we apply the lateral force, it generates a lateral traction, and that lateral traction comes out to be same as the analytical lateral traction. Also, it divides the contact region into three regions, which is first one is slipping left, first one slipping, second in middle is a stick, and on the right is also the part which is slipping. So it divides into stick slip region, and we can see a clear separation between stick and slip region. Also, when we apply two parameter friction, we see the same thing, but here we do not have any analytical expression to compare with. We can see a clear separation between stick slip boundary. We can see that the traction from the slip region is far different from the stick region, and that difference can only be seen because we used a very, very fine or extremely fine mesh for the analysis that separate both stick and slip region clearly. So another benefit of this compliance formulation is it gives us internal stresses for free, because we already know the traction on the surface, we already know the Michel coefficient, so we can easily calculate stresses inside the body or on the body and on the surface of the body, and also we can easily calculate displacement inside the body or on the surface of the body. So here we first compare the radial stress, which comes out to be almost exactly same for all three cases, because we also applied Goodman decoupling approximation. For the circumferential stress, we can see it was initially symmetric for the normal contact only, but the symmetry breaks when we applied the lateral force, and it comes out to be almost same for Coulomb of one parameter and two parameter Coulomb friction. The other stresses are shear stress and the von Mises stress that we compared here. So for the shear stress, initially it was symmetric, but as we applied the lateral load, the symmetry break in the both cases, and you can see that they are almost same, but there is only a very small difference at the contact surface. For the von Mises stress, Again, the maximum level of von Mises stress and its position change. So for the normal contact only, the von Mises stress at 0.7 A inside the body away from the contact region. And when we apply Coulomb friction, the maximum von Mises stress shift to the slipping region somewhere at 0.8 A. For the two parameter Coulomb friction, it shifts to the exactly at the stick slip boundary, somewhere around 0.6 A. And on the other hand, there is a very small difference inside the body uh, for any shears. So in conclusion, the process generate a compliance rather than a stiffness matrix, permitting the retention of only the degrees associated with the contact and an associated equation. And we can drop all the equation where the nodes are not in contact. The second thing is the strategy facilitate extremely fine meshing over the contact path, as it is necessary to simulate elastic contact over the extremely small portion of the surface for the contacting bodies. And another one is the contact analysis of two identical cylinders, which is shown here, showed a good verification of the numerical solution where the analytical solution also exists, and the comparison show uh, it shows a very good comparison between them. Also, the extremely fine mesh provides a high resolution and the sharp details of the traction distribution associated with the two parameter friction model. For the future work, this fine mesh strategy can be used as a test bed to numerically simulate contact problems to understand the effect of decoupling approximation and multiple friction model. This extremely fine mesh can be implemented with elastohydrodynamics lubricant contact for contact problems such as rotating shaft and roller bearings. And also a similar compliance matrix formulation can be designed for elastic annular disc. So thank you for listening, and now I can have your questions. Thank you again.